Hi, this is Hayden Fowler. I'll be going over question 2 of homework 9 for the extra credit video tutorial. To start, I'm going to go through the question and then break down each part. Um, Real quick, what you're going to need to know in order to do the calculations for these is um, knowing where the phasor notation thing is here. Just press Control, the little book, and then for imaginary numbers, just press this here, the little pi symbol, and then the imaginary symbol there. If you want to convert from polar to rectangular or rectangular to polar, you just press Menu, Number, Complex Number Tools, and then 6 for convert to polar, and then 7 for convert to rectangular. And then if you ever want to do complex conjugate, which there's one part in here, you just press 1 for complex conjugate. To start, the question says, for the circuit shown, a source Vs supplies through a network 3 loads connected in parallel. The voltage across the loads is known to be magnitude V1 equals 500 VMS or VRMS. It is also known that load 1 absorbs 10 kilowatts, so there's your average power here for load 1, at a power factor of 0.8 lagging, which is positive, so inductive. Load 2 absorbs 20 kilowatts and negative 15 VARs. So this is already in complex form here because you have your power for P2 and then your reactive power for Q2. Load 3 absorbs 30 kilovolt amps. So this is already in complex form. So this is our apparent power. At a power factor of 0.5 leading. So this would be negative, so capacitive. So for load 1, you start off using the P over power factor equals complex power formula. You put your 10 kilowatts over your 0.8, which gets you 12.5. Actually, that's wrong there. That should be, 12,500 volt amps. And then to find your phase angle, you use power factor equals cosine theta, and then just do arc cosine for both sides, which gets you arc cosine of the power factor gets you your phase angle, and so the arc cosine of 0.8 gets you 36.87. So here's S1. I just put it into polar form, which this would be apparent power, and then your phase angle here. Using what they gave us up here, which is the 20 kilowatts and negative 15 volt or negative 15 kilo VIRs. And then for load 3, since they essentially already put it in complex power form, I have the 30 kilovolt amps and then a negative phase angle for the arc cosine of 0.5. And then you put the negative symbol here because it is leading. So it would be negative 60. And then so to combine all your loads to get this section, this complex power section, you put STL load 1, load 2, and load 3. And then when you add those all together in the calculator using what I showed you earlier, it'll get you 56,800 or 56,088.8 with a phase angle of negative 36.65 degrees. And then using complex power equals VRMS and the complex conjugate of IRMS, switching it around to get you the complex conjugate of IRMS equals complex power over VRMS. Since we already have 500 for our VRMS, and then our complex power for the load, or for all the loads, you would just put the complex power for all the loads over VRMS, and that would get you the complex conjugate of IRMS equals 112.18 negative 36.65 degrees. And since it's the complex conjugate, you would simply just flip the sign of the phase angle for IRMS, and that would get you IRMS equals 112.18 amps with a phase angle of 36.65. Now to find the complex power of the network, we would need IRMS squared multiplied by the impedance Z of the network. And the impedance Zn is essentially just your R plus your X, which would be 1 plus J2. And once converting to polar form for this expression, you would get 2.24 ohms with a phase angle of 63.4 degrees. And since this is the magnitude of IRMS squared, you would negate the phase angle of your IRMS, and you would just leave essentially the 112.18. And so 112.18 squared times 2.24 ohms, with a phase angle of 63.4 gets you the complex power of the network, which is 28,188.9 with a phase angle of 63.4 degrees. So taking into account the complex power of the source is equal to the complex power of the network plus the complex power of the total loads, you would add both of those up, and that would get you the complex power of the source. This would be your apparent power, and then once converting into rectangular form, so polar to rectangular, this would be your average power and your reactive power. And since your reactive power is negative, it would be a leading power factor. And to find that, you'd have your average power over the magnitude of the complex power, which would get you your power factor. And if we divide both of these together, you get a power factor of 0.989. And so taking from everything we have up here, your apparent power is 58,228.6 volt amps. Your complex power is 57,643.9 watts. Your reactive power is equal to negative 8,231 VARs. And your power factor, which is leading, would be 0.989.